Friends, very good morning to everyone. Today, let us discuss with the Mitsunobu reaction. This reaction is given by Dr. Oyo Mitsunobu. Professor Oyo Mitsunobu developed this remarkable reaction, which is an useful reaction in organic chemistry. What is this Mitsunobu reaction? This is an organic reaction which converts a primary or a secondary alcohol into variety of organic compounds using diethyl azo dicarboxylate or diisopropyl azo dicarboxylate and triphenyl phosphine. Final product formed, it depends upon the variety of nucleophile we add. They are generally the conjugated acids of the nucleophile which is used. The salient feature of this reaction is that the alcohol, the primary or secondary which we use, it stereochemistry gets inverted. If I start with R configuration compound, I end with S configuration and vice versa. It is something similar to that of substitution nucleophilic bimolecular reaction, that is SN2 reaction. Now let us look into the reaction. A primary and secondary alcohol reacts with an acidic compound in the presence of diethyl aza dicarboxylate. It is given as DEAD. And triphenyl phosphine, it is can be represented as PPH3. And I get a substituted product. The OH gets removed. The hydrogen which is from the back side moves towards the front and nucleophile is attacked from the back side. Ultimately, it's a nucleophilic substitution. OH minus is replaced by Z minus, that nucleophile. And it follows SN2 reaction mechanism. That is, attack takes place from the back side. How this attack takes place? Instead of diethyl aza carboxylate, if I replace this ethyl group in diethyl aza dicarboxylate by isopropyl group over here, which is here. The ethyl group here has been replaced by isopropyl group. I'll get diisopropyl azo dicarboxylate. Let us look into the mechanism of the reaction. Here, diethyl aza dicarboxylate, owing to the electronegativity of the oxygen, pi electrons moves towards oxygen and making this carbon electron deficient. To satisfy the electron deficiency on the carbonyl carbon, pi electrons on the adjacent aza moves towards the carbon and creating, when this pi electrons moves, nitrogen becomes electron deficient. Onto this electron deficient nitrogen, the phosphine lone pair of electrons attacks on it. And a complex is formed between triphenyl phosphine and diethyl aza carboxylate. It is unstable as oxygen is monovalent over here. To regain its stability, the excess electrons in the oxygen moves back and it forms double bond with the carbon. The carbon has to maintain tetravalency, that's why pi electrons moves onto nitrogen and thus electron-rich nitrogen abstract the proton from the nucleophile and it becomes NH and it becomes stable. And the nucleophile gets released in the process. As the phosphorus has given its electron to nitrogen, phosphorus has gained electron deficiency. As it is electron deficient, it is again unstable. And to maintain its stability, it reacts with the alcohols. The lone pair of electrons and the oxygen in the alcohol gives its electrons to this electron deficient phosphorus. And it has to maintain its valency. That's why the carbon, nitrogen, and phosphorus bond breaks, and this electrons moves towards the carbonyl carbon, and the pi electrons in the carbonyl carbon moves towards oxygen. Again, oxygen, it's monovalent here and it is unstable. It has to regain its stability. That's why pi electrons moves back, and the pi electrons over here moves onto the nitrogen, and this abstract the hydrogen in the triphenyl phosphinated alcohol. The oxygen has shared its electron with phosphorus. That's why what happened? Oxygen has got electron deficiency. To satisfy this positive center on the oxygen hydrogen breaks and the electrons moves towards oxygen, giving rise to H plus, and H plus combines with N to give rise to diethyl hydrazino-carboxylate. And this is the byproduct form. The phosphonated alcohol onto this, the nucleophile attack. This phosphonated alcohol can have equilibrium between the two structures mentioned here. The phosphorus, as the electrons are given, this is electron deficient, and to satisfy the positive center, the lone pair of electrons on the oxygen moves and a double bond can exist. An equilibrium exists in between the two structures. To satisfy the positive center on the oxygen, the carbon-oxygen bond breaks and the electrons moves towards the oxygen. Once this moves, this becomes positive. As this phosphonated oxygen is towards the front side and it is bulkier, the nucleophile cannot attack from the front side, it attacks from the back side. Once this electrons moves towards oxygen, this loses as triphenyl phosphinoxide, and the nucleophile which is attacked from the back side made the hydrogen from the back move towards the front side. That's why the inversion of the configuration has occurred. We get the inverted product. This is the beauty of this reaction. Diethyl azar dicarboxylate or isopropyl azar dicarboxylate can be used to react with triphenyl phosphine, and this complex reacts with alcohol and gets it converted into corresponding inverted product. This is all about the Mitsunobu reaction mechanism. Mitsunobu reaction mechanism has good applicability in organic reactions. This has been utilized to prepare various types of aryl ethers. And this has been utilized in preparation of various alkalides starting from quinine, colchicine, morphine, strychnine, and so on and so forth. Mitsunobu reaction has been used for synthesis of various alkalides. As we know that alkalides or any natural product will be available in very small quantities. And to extract these alkalides of medicinal importance is a very challenging task, owing to its very less amount of presence in the plants. Hence, we try to synthesize these molecules of natural product origin in our laboratory. And Mitsunobu reaction has found its use in preparation of these alkalides. Hence, it has good applicability in the organic reactions. Next class, we can deal with other reactions. Till then, have a nice day. Thank you.